Welcome to Lecture 3.1, the pigeonhole principle. The pigeonhole principle is something that is usually stated without proof because it is very obvious. It says that if there are n plus 1 pigeons in n holes, then some hole contains at least 2 pigeons. So of course a picture is worth 1,000 words. Here you go. This is not a proof, but it is an illustrative example. I should say, I don't have to, but for fun, there is a dual version of the pigeonhole principle that's exactly the same. It's just semantics, where we reverse the role of pigeons and holes. And it's appropriate in certain parts of the world, especially the part of the United States that I have spent more than the last decade as of this recording. And that is, if you take a shotgun and you put n plus 1 holes in n pigeons, then some poor pigeon is going to have at least 2 holes in it. I will not include a picture of that. So in this lecture, we will see some rather surprising consequences of this seemingly simple fact. Sometimes the pigeonhole principle is phrased to be objects in boxes, but I like pigeons in holes. Okay, let's get started. We'll start simple. These first few will be merely observations. So among any 13 people, there will always be at least two, that have birthdays in the same month. So here, the people represent the pigeons, and the months represent the holes. So we're trying to put 13 pigeons into 12 holes. Here's a more fun application. It's the same idea. It's that in New York City, there are 2 non-bald people with the same number of hairs on their head. New York City has population about 8.5 million, and the average person has about 100,000 hair follicles. There might be up to 150 or 200,000 on the high side. So very clearly, there's going to be many people that have the exact same number of hairs on their head. Finally, the last example on this slide is going to be a little bit less obvious than the previous two. Here I have a class of n people. I claim that there will always be 2 with the same number of friends in the class. So instead of numbering the people, let me just give them names. So let's suppose there's Alice, there's Bob, there's Charlie, and then all the way down to Z. What's a Z name? How about Zelda? So first of all, I'm assuming that friendship is a symmetric relation, which it need not be in real life. Alice can be friends with Bob, can say she's friends with Bob, and Bob can say, well, I'm not friends with Alice. But we're going to assume that this is like maybe a social media app where 2 people are either connected or they're not. So we have, in this example, we have 26 people. So we can write down below the names how many friends they have among this group of 26. So maybe Alice has 5, maybe Bob has 12, maybe Charlie's a loner, doesn't have any, and maybe Zelda has 6. And there are n people, and in theory there are n numbers of friends that someone could have from 0 up to n minus 1, because we're assuming that you're not friends with yourself. So how do you know that you can't set this up in just a way so no 2 people have the same number of friends? Well, perhaps you see this, but if not, instead of convincing you of this right here, I'm going to, on the next slide, recast this same problem more generally in the language of graphs, or a network. So in graph theory, which is a field that we're going to study later in more detail, I claim that every graph contains 2 nodes with the same degree. Now let me explain what that is, because I have not formally defined these. So given that it's the 21st century and we are well into the internet age and the social media age, everyone, even non-math and computer science people, should have a good sense as to what a network or a graph is. So this is just a bunch of vertices or dots, or we usually call them nodes or vertices, and we connect 2 vertices. If these represent friends, then the connections if the nodes represent people, the connections might represent friends. So this is an example of a graph. So maybe this is Alice, maybe this is Bob, their friends, and maybe this is Charlie, and maybe over here this is Zelda. So that's what a graph is, and we're assuming that there are no what we call loops. So there's never going to be an edge to itself like that. So that doesn't exist. There are some graphs where you want that, but this one doesn't make sense to say Alice is friends with Alice. So that's what a graph is, and the nodes are just the dots, and we call these edges. And the degree of a vertex is how many edges are going out. So Alice, we say, this node has degree 2 because there are 2 edges right there. We say that Charlie, this has degree 3. So there's 3 edges going out here. So basically degree is the number of friends. So every graph, so here graph represents class of n people, contains 2 people with the same number of friends. So this is just a more abstract way to represent this. But the idea is the same. So if we, well, let's think about why this is. So the nodes, I'm going to give them numbers instead of names. So 1, 2, 3, 4, all the way up to n minus 1 and n, and then there should be an O, and then the number of friends, again, this is a number from, everyone is going to be from 0 up to n minus 1. So the first observation is if one of these nodes has degree 0, then what does that mean? That means it is out here and it has no friends. So if this has degree 0, then none of these nodes can have degree n minus 1. Because what does it mean to have degree 0? Let's see, degree 0 means no friends, and degree n minus 1 means friends with everyone. And these are mutually exclusive. If one person has no friends, then nobody is friends with everybody. So the observation is there cannot exist both a degree 0 node and a degree n minus 1 node. So in that case, we have 2 cases, not mutually exclusive. The first case is that the degrees are that all of the degrees are from the set 0, 1, 2, all the way up to n minus 2, or case 2 is that all of the degrees are from the set 1, 2, n minus 2, or n minus 1. And of course, maybe all the degrees are 2 or 3. Both of these are possible. So I'm not saying these are mutually exclusive, but given any graph, we can always pick at least one of these to be the case and stick with it. So in this case, in this first case, we have n minus 1 possible degrees for n nodes. So we are assigning to these n nodes, these are the pigeons. Sorry, these represent the pigeons, and the number of friends are the pigeonholes. So we're saying node 1 has 3 friends, goes in hole 3. Node 2 has 2 friends, goes in hole 2. Node 3 has 13 friends. Node 4 has 4 friends, and so So we have n holes, n pigeons, and we are assigning n minus 1, we're assigning these two n minus 1 holes. Each pigeon goes in one of these holes, 0, 1, all the way up to n minus 1. So by the pigeonhole principle, two of these nodes must belong to the same hole. In other words, have the same number of friends, or in this language, have the same degree. Okay, so we will study more about graphs later in this course. If you like this, stay tuned. Next up is a fun geometric application, which on the surface looks like it has nothing to do with putting holes in pigeons, or pigeons in holes, whichever you prefer. So this says that if you draw 5 points on a sphere, then it is always possible to cut that sphere in half so that some hemisphere contains at least 4 of those points. So I want to clarify two things. First of all, when we cut, we're cutting it in half, so we're not allowed to like saw off a little edge like this. We actually want a great circle, which is like an equatorial line, though it can be at any angle. So something like this. And next, we allow the points to be on the boundary. So if we cut along this boundary, and then two of the points, or one of the points is here, and then say 3 of them are up there, then we say that 4 of them lie in this hemisphere, because this one cannot lie on either hemisphere. Okay, one more observation. There are some configurations of points where it's really easy to see why this is true. So if we're allowed to put the points anywhere and we can put them right next to each other, then it's easy. Here the upper hemisphere will contain all 5 of them. But we aren't allowed to choose where the points go. We have an adversary that picks the points for us. It can make our jobs as tough as possible. And our goal is to show that we can always find such a cut. Okay, so let's make things hard. Let's try to put them as far apart as possible. So one goes here, one goes there. Let's put one up here, and let's put, I don't know, one in the back, say here. I'll draw it with dotted, and another one maybe in the back here. Okay, so how do we find a way to cut this sphere so that 4 of these are in 1/2 of it? So here's the trick. Let's pick 2 points, any 2 of these points. Let's just pick these 2 here, and let's connect them with a great circle. So there's always going to be one shortest path, or one which is a straight line in the sphere that goes through any 2 points. So here's that example. And now what do we have? We have 2 hemispheres, and we have 3 remaining points. So by the pigeonhole principle, one of these hemispheres will contain both of those points. And here you can see that this upper hemisphere contains that point, this point, and then these 2 points as well. So we are trying to put 3, so once we make this first cut, we're trying to put 3 pigeons in 2 holes, that is, those hemispheres. Finally, I want to mention that you could probably see how to generalize this. Instead of 5 points on a sphere and a cut containing some hemisphere containing at least 4 of them, what you can do is you can, what if you wanted to put 7 points on a sphere? So let's do the same thing. And 1, 2, 3, 4, 5, 6, 7. So now, you could, same technique, you just pick 2 of them and pick a great circle. And then what do you have left? You have 5 remaining points that you need that are divided among the 2 hemispheres. So one of the hemispheres is going to contain at least 3 points. So there we have 3, 4, 5. So a generalization of this is if you draw, or a harder example is if you draw 7 points on a sphere, some hemisphere contains at least 4. So how does this generalize? Well, let's see. So we are putting an odd number of points on a sphere. I ran out of room up top, so let me go down here. In general, we are putting an odd number of points. So let's say n points. So here, say n equals 3, and then on the top half we have 2. So this is n minus 1. So with this is n. So here's n equals 3, n equals 3 plus 1. So I claim that in general, if we put 2n plus 1 points on a sphere, then some hemisphere contains at least n of them. I'm sorry, not n of them. So here we have n below, but we have n plus 2 of them, because we have 2 of them that are on the boundary. So n plus 2 of them. And the reason why is because when we have 2n plus 1 points and we subtract 2 of them that lie on whatever great circle we choose to draw, we end up having 2n minus 1 pigeons that we have to distribute among the 2 hemispheres, the top and the bottom, or I guess one in the other. 2n minus 1 pigeons in 2 holes. So that means that some hole contains at least n. So 2n, so this is n plus n minus 1. So some hole or some hemisphere contains at least n of them, and then we already had 2 of them on that boundary anyways. So n, and then I should say plus 2 on the boundary. So this is a more general statement of this right here. That said, this here probably sounds a little more impressive because 4 is 80% of 5, where in general, n plus 2 is, you don't think of this as 80% of 2n plus 1. You think of it as slightly more than half of this. So this should not seem surprising. This one certainly does, at least at first. Our last example is to the theory of numbers. So let's let S be a set of 101 distinct integers chosen from the numbers 1 up to 200. Now there's nothing special about 101 except that it's half of 200 plus 1. So if I wanted to, I could do the same thing with 11 integers chosen from 1 up to 20. But I like 200 because it's not too big, but it's big enough that there are 10 to the 58 subsets of size 101. So 10 to the 58 possibilities for S. So what I'm about to claim, there's no way you can possibly ever check using brute force. I claim 2 things. First of all, the set S contains 2 consecutive integers. That seems reasonable, because again, I have more than half of the elements taken, so it seems like that at some point you got to have 2 in a row. But less obvious is the next one. S contains 2 integers such that one of them is divisible by the other. Now this is something that we will study in more detail, divisibility, in a few lectures, but it's also something that we all learned in grade school, so I don't think I need to define it to be able to use it in this lecture, to at least speak of it. Okay, so let's start with the first one. S contains 2 consecutive integers. So again, it's probably something you can convince yourself of just by looking at it, but let's formalize it. So I'm going to define 100 sets. So I'm going to say S1 is the set containing 1 and 2. I'm going to say S2 is the set containing 3 and 4. Let's say S3 is the set containing 5 and 6. S4 is the set containing 7 and 8, all the way up to S99, which is going to contain 197 and 198, and S100, which is going to contain 199 and 200. So I have partitioned these numbers into these 200 numbers into 100 sets, and S is a set that contains 101 distinct integers. So think of these as the pigeonholes and S as the pigeons. So we are picking 101, or we are placing 101 pigeons in these 100 holes. So at least one hole, meaning one SI, so SI, which is 2 consecutive integers, I'm not going to do the math to figure out what indices these are, must contain 2 elements from S. So that's why this is true from the pigeonhole principle. For part 2, I claim that this also follows from the pigeonhole principle, but it takes a clever setup to see how it works. So I encourage you to pause this video and see if you can figure it out. But it is one of those things that once you see it, it seems obvious, like, oh, I should have thought of that. But it's hard out of the blue to come up with it. Okay, so here's what I'm going to do. I'm going to write down a whole bunch of sets. So as before, I'm going to partition these numbers 1 up to 200 in a bunch of sets. So I'm going to start out with 1, and then I'm going to keep doubling that. 2, 4, 8, 16, 32, 64, 128, and then I'm going to stop because if I double it again, I get beyond 200. So I'm going to call this S1. My next one, so I'm going to start with the next odd number, 3, and I'm going to keep doubling that. So 3, 6, 12, 24, 48, 96, and 192, and then I'm going to stop. So I'm going to call this S3. And then S5 is 5, 10, 20, 40, 80, 160, and I think you get the idea. S7 is, I'll do one more of these, 7, 14, 28, 56, 112, and then all the way up to, let's see, so S49 is going to be 49, let's see, 49, 98, oh, that's not the one I meant to do. Oh well, 147, oh yeah, I meant to do the 49th one. I meant to do S99, or something like that, is going to be 99, 198, and then S101 is going to just be 101, and then everything beyond there up to what's the last one, S199, are just going to be singleton sets, sets with just one element. So there are 100 of these sets, right? Each one starting with one of the 100 odd numbers in S. Also, these form a partition of these 200 numbers because every number in here is in precisely one of these sets. If it's odd, it's in the beginning of one of the sets. If it's even, then it's somewhere in the middle. It's somewhere in here. And you can figure out what set it is by, let's take 80 and just divide 80 by 2. You get 40, and 20, and 10, and you do that until you get an odd number. Okay, so these are going to represent my pigeonholes. Do you see where I'm going with this? If you think you might, see if you can pause it and complete it. I invite you to do that. Okay, so we are picking 101 integers from these 100 sets, these 100 pigeonholes. So one of these sets must contain at least 2 integers. In other words, at least 2 elements from S. And notice how we've constructed this is that any 2 elements in the same SI, one of them is a multiple of the other, because we're constructing them by just multiplying by 2. So 12, 192 is a multiple of 24. 80 is a multiple of 20, and so forth. So the sets S1, S3 up to S199, I should say let's say are the 100 pigeonholes, and so how do I want to say this? And so the elements of S represent the 101 pigeons. You don't have to use this language when you do this. I think it's just more fun to write it up, and it's more memorable, and it's just easier to say sets. It's easier to say pigeons and pigeonholes than elements and subsets or containers and objects or whatever alternates, which you could. It's a little more colorful. So by the pigeonhole principle, some SI contains 2 elements of S, and in this case, one of these elements is a multiple of the other. And so I think that should be clear. And so I'm going to put an end of proof box right there. So this is one of those things that once you see it set up, it's clear. It's like, oh wow, that is very straightforward. But out of the blue, it's not easy to come up with something like this. This takes a little bit of clever thought to construct or to set up these pigeonholes just like this. The examples that we've seen of the pigeonhole principle, I chose because of their diversity. One of them was geometric, one of them was from number theory, one was from graph theory. But there are literally hundreds of more that I could have shown you. Some of them are beyond the scope of this class, but I encourage you to go on Google and just type in applications of the pigeonhole principle, and you'll find web pages that list hundreds of these things. And a lot of them are fun little clever tricks, especially like the last one that we saw. So I'm going to finish this lecture with a few generalizations of the pigeonhole principle. First one, I don't know if it has a name. I'm going to call it a stronger pigeonhole principle. So this says that if n and r are integers, and if we distribute n times r minus 1 plus 1 objects into n boxes, so if you prefer, you can call the objects pigeons and the boxes pigeonholes, then some box contains at least r objects. Now it takes a little bit of thought to wrap your head around what this is saying. So if they're as balanced as possible, then every box is going to be getting r minus 1 objects, and then one of them gets placed in the unlucky crowded box with r pigeons. If you didn't wrap your head around the statement above, namely this n times r minus 1 plus 1, that's fine. I think it will be clear with this example. So in any group of 25 people, at least 3 of them were born in the same month. And that makes sense because the worst case scenario in some sense is the first 24 were all born in 2 per month, and then the last one has to match up with some month that's going to have at least 3 people born in it. And notice what 25 is. 25 is 12 times 3 minus 1, so this is 24 that I mentioned, plus 1 more. So 12 represents the number of pigeonholes, and this 25 represents the number of pigeons. If we extrapolate this to a bigger group of people, suppose we have a school of 24,156 students, which is 366, the number of days in a year, counting leap day, times 67 minus 1 plus 1. So if we have this many students, then at least 67 of them will share a birthday. So in any university with more than 24,156 students, you will, at the worst case scenario, have at least 67 with the same birthday. Finally, I will conclude this lecture with what is actually called the strong pigeonhole principle, which is a generalization of this statement above, which is why I didn't call this one the strong pigeonhole principle. I just called it a stronger version of it. This is the strongest. So this says that if we have n positive integers, q1 up to qn, and we have n boxes or n pigeonholes, then if we add up those integers, we subtract n, and we add 1, we take this many pigeons and put them into the n boxes, then either the first box contains q1 objects, or the second box contains q2 objects, or the nth box contains qn objects. So this is notationally a little bit of a nightmare, but once you wrap your head around it, pause this lecture, and if you don't quite see it yet, it's actually fairly intuitive. So here's a picture of this. So here's maybe you have q1 pigeons, or let's say balls in here. So let's start, to motivate this, let's start with q1 balls in here. Let's start with maybe q2 balls in here, maybe q3 only is 1, and then up to qn, maybe you have, I don't know, something like this. So we start with this many balls. So remember, the conclusion is we want at least this many balls in bucket 1, or this many balls in bucket 2, or this many balls in bucket 3, or this many balls in bucket n. So let's start with when all of these things are satisfied. And now I am going to take away only one ball in every single bucket. So now none of these objectives are satisfied, but as minimally as possible. So here we have q1 minus 1 balls, and that bucket is full. And we have q2 minus 1 balls, and we have q3 minus 1 balls, and we have qn minus 1 balls. So overall we have q1 plus all the way up to qn minus n balls that we have taken away. And this is the case where all of the buckets are completely full. If we add any one more ball, and here is what we do, that is that last pigeon that gets stuffed into one of these buckets, and whichever bucket that is, if it's in the first bucket, then the first bucket contains at least q1 objects. If it's in the second bucket, that contains at least q2, and so forth. Okay, so I'm not going to do any applications of the strong pigeonhole principle, but I encourage you to try to come up with some yourself. They're not quite as normal or quite as natural, I think, as maybe this example with people born in a certain month, or with the regular pigeonhole principle, but it is a natural generalization. Notice that the special case of when all of the QIs are equal to 1 is just the standard pigeonhole principle that we started with. And the special case of all of the QIs being equal to R yields the so-called stronger pigeonhole principle, not the strongest, the stronger one that's listed up here. Okay, that's it. Tune in next time, where we will be studying more on the theory of numbers. We'll start with parity, even and oddness, and then look at prime and composite numbers and factorization. And the pigeonhole principle that we studied here is going to be a tool that we might use along the way in some proofs. So stay with us.